All right. So last time we had discussed the proof of Merarys theorem, which says that if you have a continuous function on a domain and the integral around every rectangle that's contained in the domain is 0, then that function is holomorphic. And so in particular, analytic functions, the integral of those around rectangles are 0. So any analytic function has to be holomorphic. So that was integral to our proof that analytic functions are holomorphic. And the way we showed that was by showing that that continuous function in Merarys theorem has to have a local antiderivative. So any analytic function on a domain has a local antiderivative. So what we did was we took a small disk inside our domain around a point and then showed that we could find a function capital F whose derivative was our starting function, little f, on that disk. Okay, so that was what we did last time. So we know that analytic functions, at least locally, they have antiderivatives. We define them. We define that local antiderivative sort of by analogy with calculus, by analogy with the fundamental theorem of calculus, part 1. All right, but it's important to realize that an analytic function doesn't have to have an antiderivative on its whole domain. So the most natural example to consider is 1 over z, the simplest non-trivial rational function. So the natural domain of this function is the non-zero complex numbers, c star. And it's pretty easy to see that there can't be a antiderivative on all of this domain for 1 over z. And the way you can do that is integrate around the unit circle and compute that integral two different ways. So there was a homework assignment that you did that showed that if you have an analytic function which has an antiderivative, then you can compute the derivative, the integral, the line integral of that analytic function by basically using the fundamental theorem of calculus part 2. So just by evaluating that antiderivative at the endpoints and subtracting. So that's what we're using for the first computation, which is here. So the integral of 1 over z, if there was an antiderivative, it would just be f, that capital F evaluated at the endpoints. But since our curve is closed, the endpoint and the starting point are the same. We can take that to be the point 1 there on the unit circle. And so that difference is 0. But it's easy to compute, and we've done it before in class. We've even computed more general things, that the integral of 1 over z around a simple closed curve going around 0 is 2 pi I, and that's not equal to 0. And so this contradiction shows that you can't have an antiderivative on all of the domain. However, if you just kind of ignore this subtlety, and I asked you for the derivative of 1 over, or the antiderivative of 1 over z, you would tell me that it was log z. And you're almost right. You just have to be careful about domain issues, as well as this computation indicates. So if we go to a smaller domain, so we shrink our domain D to D prime, which is the complex numbers minus any ray extending from the origin, then we can define a branch of the logarithm on that domain. And we know that the logarithm, whatever branch you pick, the derivative is 1 over z. Okay, so we do have an antiderivative on this smaller domain, and we don't get a contradiction like before because we can't draw a simple curve in d prime that goes around the point z equals 0 like we did above, right? So if your simple closed curve doesn't go around z equals 0, then the integral is 0, and you don't get any contradiction. You can just you can just apply complex Green's theorem to see that, because 1 over z is analytic away from the origin. Okay, so the key thing is that this domain, the smaller domain d prime, if you draw a simple curve in it, the interior of that simple curve, which I've illustrated in this picture here, the interior lies in that domain d prime. And this is in contrast to the domain d, where any simple closed curve going around the origin, the interior of that curve has points that are not in the domain, right? It has the point 0, which is not in the domain of the function. Okay, so basically it turns out that this kind of sort of what you might think of as like a geometrical property of the domain, really properly we would call it a topological property of the domain, but that's probably for a future math course. So it has something to do with sort of the shape of the domain. So the domain D has this property that you can draw loops that sort of encircle points outside the domain, whereas D prime, any loops you draw in the domain only encircle points in the domain. And so this turns out to be the only obstruction to defining an antiderivative of an analytic function. So if you have an analytic function on the right kind of domain, then you can always define an antiderivative. Okay, so that's what we're going for next, and we'll just make a quick definition and then look at a result. So here's the definition of the type of domain we want to look at. A domain D is simply connected if the interior omega of any simple closed curve gamma, where this gamma is contained in D, is such that omega is also contained in D. Okay, so if you draw a non-intersecting closed curve in your domain, to be simply connected, you need all of the stuff that is contained inside that curve to also be in the domain. So that's what we mean by simply connected. Okay, and then the theorem is that an analytic function on a simply connected domain D has an antiderivative. Okay, now I don't like doing this generally, but I can't give a really complete proof of this. Turns out the complete proof of it is kind of annoying. Not really that difficult, just annoying and unworthy of all of the full effort to prove it. But I can indicate very well why this result is true. Okay, so we'll define analytic function, little f. So define capital F of z to be equal to the integral along gamma, I'll tell you what gamma is in a second, of f of zeta d zeta, where gamma is any polygonal curve from some fixed z naught in D to Z. Okay, so what you do is you fix arbitrarily a point z naught in your domain, and then you look at any polygonal curve whatsoever that connects z naught to z, which we can do because we're working with a domain, which is any 2 points in a domain are connected by a polygonal curve by assumption. And then you just integrate your function little f along that, and that gives you your function big F. Okay, and so the picture is like this. So you have your z naught here and your z over here. All right, and then you have a polygonal curve. You pick any polygonal curve you want, gamma, and take the integral of your little f along that polygonal curve. Okay, so there is something of an issue here. There's no canonical curve gamma between a given z naught and z if you just define some random simply connected domain D. So we're allowing this gamma to be arbitrary here, and what we have to show is that our function capital F is well defined. So what we have to show is that it doesn't depend on the choice of gamma. So if we were to take another curve, so if I were to take another polygonal curve like this, gamma prime, I want to show that, so first thing is I need to show that F is well defined. I.e. independent of polygonal curve. So that is, I want to show that the integral along gamma of little f d zeta is equal to the integral along gamma prime of f d zeta. Okay, and so this will be the case. So this is the case if and only if the integral along gamma minus gamma prime of f of zeta d zeta is equal to 0. All right, so this, so note that gamma minus gamma prime is a closed polygonal curve. So it suffices to show that the integral of f of zeta d zeta around sigma is equal to 0 for any closed polygonal curve sigma. Okay, so what we have here, I guess I could just to make my picture again, is that yeah, so now we have some just polygonal curve Okay, and there's our starting and ending point there. Okay, so we need to show, we need to argue that the integral around any such closed polygonal curve is equal to 0. And the picture indicates the argument. Because, so basically, the integral, basic claim is that the integral of sigma over sigma of f, that we can break sigma up. So let me see here. Sorry. So as you're going along here, you can add in these extra points where you have intersections. So you have the vertices of each of the. So if you mark the vertices, so you have a vertex here and here, but then you also add in these intersection points. So you have an intersection point, intersection, then a vertex, intersection, vertex, 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 same intersection again. And you just kind of go around like this. And you're back. Then that would give you... So now if you look at all of the little curves that you get by going between all of those black dots, so you can write this sort of as a sum over smaller curves, sigma I, which are those little segments going between the black dots in the picture. Okay, so like, so this might be a little piece of sigma I there. And then if you rearrange these appropriately, then you can group them together so like in this picture here, you have this group. So 1, 2, 3, 4, and they bound so that makes a little closed loop there, a simple closed loop, right? So this makes a closed loop that doesn't self-intersect. So the whole big green curve, that had a lot of self-intersections, but this little circuit here with these 4 smaller curves is a simple closed curve, right? And so if we just focus on the integrals of those 4 small green curves there, we can use complex Green's theorem to turn that into a surface integral, right? But then the fact that we're assuming that our domain is simply connected, since this is a simple closed curve, that interior part, that has to be contained inside the domain itself, right? So that's why we can apply Green's theorem, a complex Green's theorem. And then because our function is analytic, well, first of all, we now know that analytic functions have continuous derivatives, so applying Green's theorem is legitimate. And also, we know the integrand in Green's theorem is equal to 0. So that those surface integrals, or sorry, those area integrals are going to be equal to 0. And you also, right, so you can sort of go around and do this. So you have this little circuit in here, and that gives you a surface integral. And you have this circuit here. Sorry, I keep saying surface integral, area integral, whatever. So you have all these little area integrals. So the claim is that you can turn this into a bunch of area integrals, right, over some polygonal regions. So over some regions, I don't know, we'll just call them R sub j. And yeah, so those are going to be surface integrals of df dz bar, and then I guess times 2I. That's complex Green's theorem, dx dy, and this is equal to 0. So this is just going to be 0 as claimed. So that's the basic idea. Well, okay, and so you can make that rigorous. It's not that bad to make it rigorous with induction, as long as the self-intersections of your polygonal curve are not too are point-like this, as long as the self-intersections are these simple points. But the problem is you can draw a different kind of closed polygonal curve that looks something like this. So you could have like this segment, then this one, there, and then you can, in this segment, you could sort of trace back over part of what you already did. So right here, where I'm thickening it up, you've doubled back along somewhere you've already been. So your intersection is this whole segment instead of just these points. So making sure that you're thinking through all the details correctly and making sure those types of intersections aren't going to present a problem it just takes a little bit of effort to make sure that argument definitely goes through. So you could have these more problematic looking intersections where like you sort of go forward and then back in your curve. Okay, so the full argument. So this isn't really a full rigorous argument, but I think it's good enough to sort of give you the idea. Okay, and so that's all I'm going to say about why this is this function f is well defined. Okay, so it's basically, so the spirit of the argument is that you just take this closed curve and then you turn it into some area integrals and then use Green's theorem. All right, so the second thing is that, well, we have to show that big F is actually an antiderivative of our given function. So we need to show that big F prime of z is equal to f of z. Okay, and this is very similar. It's actually easier than the argument. We have a little bit more flexibility because we're using polygonal curves and not just purely curves that go horizontal and vertical like we were in Merarys theorem. So again, I'll draw my simply connected region and my z naught and then my z, and I have a curve I got a polygonal curve, and so that's f of z. So what we're going to do is we need to check that the limit. Let me write down first what we have to check. I should have done that first. Limit as h goes to 0 of f of z plus h, big F minus big F of z over h, and then minus f, little f of z, right? Because this is our claimed derivative. We want this limit to be equal to 0. Okay, and that'll be the same as if we just do the just absolute value. Okay, so the first thing we'll look at is f of z plus h minus f of z. Okay, so I need a z plus h, and so let me put z plus h here. Okay, and so f of z plus h, well, how do I represent that? F of z plus h is an integral along a polygonal curve of our little f function. So let's say maybe this is the polygonal curve. Okay. And then, so this f of z plus h minus f of z, that's represented by an integral So let me write this out. Let's see, just to make sure everybody can follow this. So let's call our red curve gamma 1 and our blue curve gamma 2, or yeah, okay, whatever. So this is the integral around gamma 2 of f of zeta d zeta minus the integral around gamma 1 along gamma 1 of f of zeta d zeta. And that's the integral along gamma 2 minus gamma 1 of f of zeta d zeta. And gamma 2 minus gamma 1 right, so the way we can think of that is we can think of minus gamma 1 followed up by gamma 2. So let me now, in the picture, draw that. So this is going to go backwards along gamma 1. And then forwards along gamma 2. Okay. So that's what our that's what f of z plus h minus f of z looks like. It looks like this integral along this yellow curve from z to z plus h. This complicated long yellow curve. But what we can do is if we take that yellow curve and we just add this straight segment here onto it, right, that would be equal to 0. So let me call that gamma 3. Right, so what we would have is that the integral right, because we argued above that the integral around any closed polygonal curve is equal to 0 in this simply connected region, right? So minus gamma 1 plus gamma 2 plus gamma 3, the integral of f around that is equal to 0. So that means that the integral of f along gamma 1 minus gamma 1 plus gamma 2, that's equal to the integral along negative gamma 3 of f of zeta d zeta. Right? So let's see. Make sure I don't erase too much here. And so our negative gamma 3, that goes just the other way, from z straight to z plus h. Okay, so this integral here is equal to the integral along negative gamma 3 of f of zeta d zeta. Okay. Right. So back to the computation of the limit. So thus the limit as h goes to 0 of, so we have 1 over h times e. So we have f of z plus h minus f of z over h minus little f of z. That's equal to the limit as h goes to 0 of 1 over h times the integral along negative gamma 3 of f of zeta d zeta minus f of z. And then this is like in Merarys theorem. So what we're going to do is just rewrite that constant there. So that constant is actually the same thing. So f of z being a constant is 1 over h times the integral along negative gamma 3 of just that constant with respect to d zeta. Okay, because you can pull that constant out, and then the integral of 1 along that curve, well, 1 has an antiderivative, it's just zeta, and so we evaluate along at the endpoints z plus h minus z, and that's just h. So that h divided by h just gives you 1, and then you're multiplying that by f of z, you just get f of z back. Okay, so that's just a simple little computation, and so this is the limit as h goes to 0 of 1 over norm h times the absolute value of the integral along negative gamma 3 of f of zeta minus f of z d zeta. And then a typical application of the max length inequality shows that this is less than or equal to. So the length of negative gamma 3, well, that's just h. Right? So that's just the length of h. And then you have the max along that curve. So the max of the absolute value of f of zeta minus f of z. That curve, that just extends a distance of h from z. So we can just say that this is the max in the closed disk around z of radius norm h. Okay, and well, so these h's cancel, and then that maximum, well, since f is continuous at z, f of zeta has to be getting arbitrarily close to f of z as zeta goes to z. And so this is just equal to 0 by continuity of f at z. All right. And so that establishes that f prime is equal to f. Okay, so thus big F prime is equal to f. Okay. So that shows on a simply connected domain, an analytic function has an antiderivative. And the place where we use the simply connected is to show this, that the integral around any closed polygonal curve is equal to 0. And so when we had a closed polygonal curve, we could split it up into little pieces so that you were looking at these parts that bound these simple little pieces that are not intersecting, and those thus have to bound parts of the domain because of the simply connected hypothesis. So we could use Green's theorem there. That was a basic place where we used the simply connectedness, there, where that came in a crucial way. All right. And then just a little corollary of this. So corollary, and I'll just refer to this as strong Cochise theorem. I don't think this is in the book, but this is just a simple application of what we just did. So this reads that, so in Cochise theorem, you look at the integral of an analytic function around a simple closed curve and conclude that that's 0. And we needed the simple part because we applied Green's theorem. So we need to apply Green's theorem to the interior of that simple closed curve. So we have intersections, things become complicated. But this will be able to drop the simple closed curve as long as our where we're looking is simply connected. So if f is analytic on a domain D, and D prime contained in D is a simply connected domain. Then for any piecewise smooth closed curve, which is contained in that simply connected part, the integral around gamma of f is equal to 0. Okay, and the proof is amazingly simple. So little f has an antiderivative, big F, on d prime. So the integral around gamma of f of z dz is just equal to capital F at gamma at some time. It doesn't really matter. It's going to go back around to the same point, minus f of gamma at c, and that's equal to 0. Okay, so we use that we have a closed curve there. Okay. Right, so your curve can look particularly nasty. So there are examples of curves that intersect infinitely many times. So note, gamma can have infinitely many self-intersections. So it can be pretty bad. You can cook up an example by looking at the graph of the function like x times sine of 1 over x or something like that from calculus, because that graph has intersects the x-axis infinitely often. So it's some crazy looking thing so you got x and negative x here, and it does some crazy oscillating thing, and then it oscillates a lot, infinitely many times, and you can just now think of this as the complex plane. So there's your x and your y, real imaginary axis, and you can take this. Yeah, so you can have this curve like. So then you can break off from the graph at some point, say like here, and like circle back around and come through like this, and then come straight along the x-axis. So make that your curve, and that would be a pretty bad example, but for which you could still apply this stronger form of Cochise theorem to this curve gamma here. Even though it has infinitely many self-intersections. All right. So next we're going to look at the zeros and singularities of an analytic function. First, the zeros. Okay, and so we're going to start in the following way. So suppose f is analytic on a domain D, and we have a disk, so we'll fix a disk around a point of a particular radius that fits inside that domain. And since our function's analytic, and we are working on a disk inside the domain, we can write f in a power series. So write f of z equals sum from n equals 0 to infinity, a sub n, z minus z naught to the n. And this is in the disk, of course. Okay, so one thing we can observe from this, that if the a's equal 0 for all k, then f is identically 0 in the disk. Right. So that's simple enough. But what did this say? So observe that that's the case, and that a sub k equals 0. Remember, the a sub k are the kth derivatives of f at z naught divided by k factorial. So a sub k equal to 0, that's equivalent to saying that the kth derivative of f at z naught equals 0. Right? So one thing we can conclude from this is that if every derivative of an analytic function vanishes at a point z naught in its domain, then f vanishes in any disk centered at that point, which fits inside the domain. Okay, so that's just what that says in words. Okay, so f vanishes identically. So maybe I'll be more precise about that. Okay, so f is identically equal to 0 in any disk that's around that point that fits in the domain. And in fact, it follows that f is identically 0 in all of D. And well, so why is that the case? Turns out it's actually a little bit complicated. So here's sort of the basic situation. So let's say this is D. And let's say our starting point Z naught is here. Okay, so Z naught is there. And we can, if we draw a disk around Z naught, then our function is identically 0 inside that disk, right? Identically 0 in there. And so what happens is if we take another point in this disk, so let's say Z1 right there, and then we draw a disk around that, well, see, our function Z1 at Z1 we know our function is identically 0, right, in a neighborhood of that point z1. So if it's identically constantly equal to 0, then its value and all of its derivatives are all 0 as well, right? So we can use our z1 satisfies the same conditions that z0 did, right? So in any disk that we can fit in the domain around z0, our function is going to be identically 0 in that disk as well, right? And so we can keep making these chains of disks. So we can take a z2 like right here, right? And then any disk that we can fit into the domain around that point, our function is going to be identically 0 there. And so we can take another point here, and we can start chaining disks together. And the claim is that, well, by chaining disks together, we can get from any point z0 to any other point. So if we take an arbitrary point w in our domain, the basic claim is that we can get a chain of disks like this that travels from z0 to w. And, well, what we know is that in our domain, we can always connect z0, our starting point z0 to w, with a polygonal path, right? So we can take a polygonal path like this that goes from z0 to w. So as long as we can cover this polygonal path with disks, then would be done. And well, to cover a polygonal path with disks, all you have to do is to cover any particular line segment along it with disks. But it actually is surprisingly subtle to prove that you can find a chain of disks, a finite chain of disks going along a line segment like this in your domain, because to sort of exaggerate things and sort of see the problem, imagine your domain is like this, and your z0 is here, and your w is here, and you have this straight line segment. Yeah, it's not so good. So you have a straight line segment. Connecting z0 to w like this. You have to, so you start making your disks. So you make your first disk, you make this relatively big, right? And then your next point here. Now that disk has to be smaller because you're getting to this point where your domain is narrowing. And then your next disk is going to have to be fairly small as well. And your next disk is going to have to be even smaller. Right, and then your disks keep getting smaller and smaller. And the problem you'd want to worry about is that, well, is it the case that, it might be the case that you have some weird domain where you have to take your disks smaller and smaller and smaller, and then you might never get from z0 to w if your domain is really narrow and you end up needing an infinite number of disks, say. And so it turns out that doesn't happen. So there's sort of a smallest, so you never need disks smaller than some smallest radius. So there's a smallest radius for which you don't have to use disks smaller than that. And then if you have a smallest radius for your disks, then you can get across this line segment with finitely many disks, and things will work out. But that's a kind of subtle point, and you wouldn't address that until you saw a topology course. So the full proof that your function vanishes in all of D is a little bit obscured from us at the moment. But that's kind of the basic flavor of the idea of it. All right. So the basic point is that that the only way you can have, so the only ak equals 0 for all k in a power series expansion is if f is identically equal to 0 on its domain. Okay. So in other words, so the way we're going to use this is if we have a function that's not identically equal to 0, but it is equal to 0 at some point, what we can say is that not all of the power series coefficients are going to be equal to 0. There has to be some power series coefficient which is not equal to 0, and we'll use that to define a certain concept about the zeros of an analytic function. Okay, so thus, if f is not identically equal to 0 on a domain, but f does vanish at some point. And so what we're interested in is the places where our analytic function does vanish in the non-trivial situation where the function is not identically equal to 0 itself. But f of z naught equals 0, then a sub k is not equal to 0 for some k. Right? Because if they were equal to 0 for all k, then our function would have to be identically 0 by the argument above. Okay. So thus, there is a smallest m, which is a natural number, such that a sub m is not equal to 0. And so there's got to be a first coefficient that's not equal to 0 in the power series expansion. And note this m in the natural numbers, m is bigger than 0. So it can't be that a sub 0 is not equal to 0 because the function vanishes at 0. And the function vanishing at 0, that's saying a constant term in the power series expansion is equal to 0. Okay, so there's going to be some one of these coefficients past the 0th one, which is not equal to 0. And this m, so this m is called the order of the 0 at z naught. Okay, so what we can do is write our f of z. So we expand in a power series around this point where our function f is 0, and so this is n equals 0 to infinity a sub n z minus z naught to the n. Well, a sub m, that's the first one where this where the a's aren't equal to 0. So we can start from n equals m to infinity. And if m is the order of our 0. And so this looks like z minus z naught to the m. We can pull that out, and you find is a sub And so that looks like z minus z naught to the m times a sub m plus a sub m plus 1 times z minus z naught plus a sub m plus 2 z minus z naught squared plus etc. Okay. And we can call this, so remember this a sub m, that's the first coefficient in the power series expansion which is not equal to 0. And if we call this analytic function here, which is defined by that power series in this in the disk that we're working in, if we call that g of z, then we find that our f of z is equal to z minus z naught to the m times g of z, where g at z naught, which is equal to a sub m, that's not equal to 0. All right, and g is analytic here, so this is analytic. So when you have a 0 of an analytic function, there's always some characteristic m where you can factor out z minus z naught to the m, and what's left is an analytic function which is not equal to 0 at your point. Okay, so you can always factor your f as a simple polynomial times an analytic function which does not vanish at your point. Okay. So just do a quick example. Find the order of the 0 of cosine of z minus 1 at z equals 0. Okay, so cosine of 0 minus 1 is of course 0. Right, so 0 is a 0 of this function. And what you can note here is so the order is equal to m. That's equivalent to saying that a sub m is the first non-zero power series coefficient. So first non-zero a sub k, right, in the power series expansion. But a sub m, that's the same thing as the mth derivative of f at z naught divided by m factorial. So it's equivalent to, okay, so maybe I'll say it this way. So noting that a sub m is equal to the mth derivative divided by m factorial, this is equivalent to saying that that the mth derivative of f at z naught is the first non-zero derivative of f at z naught. Okay. So all we have to do here is take derivatives of our function. So I'll call this f of z. So f prime of z, that's equal to a negative sine of z, right? And plugging in 0, we get 0. So that's a 0 derivative. So we're looking for the first non-zero derivative. So if we take the second derivative, that is equal to negative cosine of z. And of course, that evaluated at 0 is negative 1. And so that's the first non-zero derivative. And so that implies that the order of the 0 at 0 is 2. Okay, because we had to go to the second derivative to get a non-zero value for the derivative at that center point. All right. So that's how you can compute the order of a zero. Okay, so here's a fun theorem that we get from this simple analysis. So just remind you that so the basic analysis is that if m is the order of a zero, that we can write our analytic function as this simple polynomial of degree m times a analytic function which is not zero at the point. So here's the theorem: if f of z is analytic, f of z naught is equal to 0, and f is not identically equal to 0, then there is a delta greater than 0 such that z naught is the only 0 of f in the disk around z naught of radius delta. Okay, so remark. So in other words, we can isolate this 0 z naught from any other 0 of our function f. And so we don't have our 0 at z naught and then a sequence of other zeros approaching that 0. We can put a disk around z naught that protects z naught from any other possible 0 of our function f. So it's isolated from other zeros. So that's the terminology. We say that the zeros of an analytic function are isolated. Well, I guess to be precise, of a non-trivial, that is, a not identically 0 analytic function are isolated. Okay, so the proof is, so write as above, f of z is z minus z naught to the m times g of z, where g of z naught is not equal to 0 in, and this holds in some disk, right? So in some small enough disk. And the rest of the proof is to just basically use the fact that since this is not equal to 0, we can find some neighborhood around z naught where g is not equal to 0 in that neighborhood. And that's just by continuity. So if g attains a non-zero value at z naught, then if you move just a little bit away from z naught, you can't move too far from this non-zero value, right? So in some small enough neighborhood of z naught, you can't sort of instantaneously jump to 0. So since g is continuous at z naught, letting epsilon equal the norm of g of z naught over 2, we can find delta greater than 0 such that when z is close to z naught by delta, then g of z and g of z naught are close together by g of z naught, an absolute value over 2. So this just means, right, so if g of z naught is not equal to 0. So let me just mock up a picture real quick here. So g of z naught is not equal to 0, right? And then if you don't, so we've picked our z such that g of z doesn't stray from g of z naught by more than the length of g of z naught over 2, right? In other words, we've arranged things so that our g of z falls in the, so if this is the distance from g of z naught to the origin, here's the midpoint there. That's at a distance of g of z naught over 2. We've arranged things so that our g of z falls in this disk around g of z naught of that radius. But in particular, in this disk, g of z is not equal to 0, right? So g of z lies in this disk, and so it's not equal to 0. And that's the key thing. So g of z is not equal to 0. In particular, g of z does not equal 0 in the disk around z naught of radius delta. Right, and then since z minus z naught to the m equals 0 if and only if z equals z naught, the function f of z, which is the product of these two things. And so z minus z naught to the m, that's equal to 0 only at z naught. And g of z is not equal to 0 at all in this small disk of radius delta. So this function f of z is 0 only at z equals z naught in the disk around z naught of radius delta. Okay, so you basically use the fact that g is not 0 at z naught and then use continuity to restrict to a small enough disk to say that g is not equal to 0 in that disk, and then use the fact that the only 0 of this polynomial here is at z naught. Right, so the only place where the product can be equal to 0 is at z naught. Okay, and that's what we wanted to prove, right? Z naught is the only 0 in that disk. So our 0 at z naught is isolated. Okay. And the cool corollary of this is that if f is analytic on a domain D, and we have a sequence of points converging to some z, so the z sub n's, those are in the domain, z is in the domain, and f of z sub n is equal to 0 for all n, then actually f is identically equal to 0 on D. And the proof is simple. So because f is analytic, so by continuity, f at z, that's the limit as n goes to infinity of f of z sub n, which is equal to 0. So z is a 0 of our function f, right? So z is a 0 of f, but it's not isolated. So by the contrapositive of the last theorem. And so by the contrapositive of the last theorem, so basically this said that if you have a not identically zero analytic function and you're looking at a zero of it, that has to be isolated. So if you have a zero of your analytic function which is not isolated, then the inevitable conclusion is that the function has to be identically equal to zero. So by the contrapositive of the last theorem, f is identically equal to zero. Okay, right. So just knowing that you have, if you have these zeros of your analytic function and they're bunching up and limiting to a point, then your function has to be identically equal to zero. So just knowing that your analytic function is zero at a certain subset of points, just countable subset of points, allows you to conclude that your function has to be equal to zero everywhere. So this is a more evidence of the rigidity of analytic functions. So they're sort of rigidly defined in this way. Okay. So one quick remark I want to make. Is that the limit point z must be in D for the conclusion to hold, for the conclusion of the corollary. So one example to see this is to think about sine of pi over z. So in this case, so f is equal to 0 at all 1 over n, right? Because that gives you sine of n pi, and 1 over n approaches 0, right? So you have this. So you have all these zeros which are limiting to the point 0, but your function is not defined at this limit point 0, right? That 0 is outside of the domain. So we don't get any contradiction from the fact that this function is not identically 0, right? So if you tried to apply this corollary to this function f, you would seem to get a contradiction, but there is no contradiction because part of the assumption is that this limit point be in the domain of the function, and the limit point in this example is not in the domain of the function. And also a remark too is that you can contrast this behavior of analytic functions with real differentiable functions. So for example, you can consider the function of x, real variable x, x squared times sine of pi over x for x not equal to 0 and 0 when x equals 0. And this is differentiable, so this is differentiable everywhere. Not constant, non-constant. And x equals 0 is a non-isolated 0. Okay, so being differentiable for a real function, you can have non-isolated zeros, a sequence of points where your function is 0, limiting to a point where your function is 0, but not have a constant function. And incidentally, so if you try to take this real function here and just make a complex valued function out of it by doing this, then this cannot be an analytic function, is not analytic. and that's by this corollary. So if you try to, and so you're going to have less luck defining analytic functions by piecewise type constructions like this than for real valued functions, because so this function, if it were analytic, this the zero at 0 would have to be isolated, which it's not. Because again, this function at all of the 1 over n's is equal to 0. So this corollary shows that this function here cannot possibly be analytic. Okay, that's going to do it for now.